Homework 13, section 7.1, the standard normal curve 2. In the previous video, I neglected to mention something very important, that the histogram was a relative frequency histogram. And remember, the relative frequency is just the frequency divided by the total number of observations. And what it basically told us is what percent of a data set fell within a given class. So for example, if the relative frequency for a certain class was 0.35, that means that 35% of the data fell within that class. So, we have an infinite number of really skinny rectangles, and they smooth out into what's called a probability density curve. As the class width approaches 0, and I only put the word approaches in quotes because in calculus it has a rigid definition, but we'll just think about it intuitively. As the class width gets closer and closer to 0, the polygon smooths out. And again, the word smooths out has a rigid definition in calculus, but intuitively it just means no corners. The polygon smooths out into a smooth curve with no corners. This is called a probability density curve. And I have a picture of one drawn here. If you happen to have your textbook, this is the same one that is drawn on page 295 in example 7.1. So what does a probability density curve tell us? Well, in a histogram, the relative frequency tells you the probability of a value falling within that class. For example, if using the same relative frequency as before, if we have a class from 2 to 3, so really it would be from 2 to 2.9 because 3 would be the next lower limit, then if its relative frequency was 0.35, that means that 35% of the data is between 2 and 2.9 or 2.99, whatever precision we're using. That also means that if you select a value at random, there's a 35% chance or a 35% probability that it would be in that particular class. So how do we do that here where we have a smooth curve? Well, the advantage to having a probability density curve is, although you've lost all of the classes because they all got infinitely thin, it allows us to calculate the probability over any interval, as if we could set up any class wherever we want. For example, let's say that we shoot a vertical line straight up from 4 and a vertical line straight up from 6. How can we use this to calculate the probability that a value would be between 4 and 6? Well, here's how probability density curves work. There are two properties of probability density curves. Number one, the total area underneath the curve is equal to 1. Total area is equal to 1, or 1.00 if you will. As a percent, that means 100, which kind of makes sense because if you go back to the histograms, the relative frequency histograms, each relative frequency represents the percent of the data inside of that class. And so together they should all represent 100% of the data. So the sum of their relative frequencies should be 1, or as a percent, 100%. That property is preserved when we make the transition from a finite number of rectangles to an infinite number, and hence a probability distribution curve, that the total area is 1, or 100%. The other property is the area between two values will represent the probability of being between those two values. Specifically, the area between, we'll say A and B. In this problem, we'll have A equals 4 and B equals 6, but we'll get back to that in a second. The area between A and B equals the probability that a value, we'll call that value X, is greater than or equal to A, but simultaneously less than or equal to B. And another way of translating that is saying that the area represents the percent of the data that's between those two values. So for example, in this case, let's say that this area shaded between 4 and 6, let's say this area is equal to 0.16. How we get that area, we'll talk about that later. If that area between 4 and 6 underneath this probability density curve is 0.16, that means that the probability of a value being greater than or equal to 4 or less than or equal to 6 is 0.16 or 16%. So a probability density curve doesn't give us a probability for a single value. It gives us the probability of being between two values. What is the probability of being a single value? Well, let's think about it for a second. For example, let's say we ask the question, what's the probability x is equal to 6 in whatever this distribution is? Well, imagine taking this vertical line above 4 and moving it closer and closer to the 6. In order to be equal to 6, you have to be simultaneously greater than or equal to 6 and less than or equal to 6. In other words, the probability that x is equal to 6 is the exact same as the probability that 6 is less than or equal to x, which is less than or equal to 6. There's only one number that can be greater than or equal to 6 and simultaneously less than or equal to 6, and that number is 6. What would happen to this area if we left the right red line alone, but we could slide the left red line closer to it? The area would get smaller, and when the lines met, the area would actually be 0. Now, if you're thinking, wait a minute, wouldn't that line be kind of thin and have some area? No. Geometrically speaking, a line has no width. It only looks like it because of the writing utensil that I'm using, but a line by definition has a single dimension, how long it is. It has no width. So if we collapse the red line over, the left red line over to the right red line, then the area in between would become 0, and this probability would be 0. Let's list this under the properties. Well, it's not really a property of the curve, it's more a property of probability. So we'll just say also the probability that x equals one value is always going to be 0. Think of it this way. In class, I think I gave an example where I said, who's 6 feet tall, 72 inches tall? And somebody raised their hand. And I said, so you're exactly 72 inches tall? And they said, yes. And I said, you're not 72.1 or 72.05 or 72 or 71.98, at which point they said, well, I don't know. And so my reply was, okay, when you say you're 72 inches tall, what you really mean is that you're in a range of values, and we just say 72. Usually it would be between 71.5 and 72.5, those would round down to 72. But because of the precision of continuous data, meaning that you can measure it to as many decimal places as you want, it's technically impossible to be exactly 72 inches tall. You're just approximately 72 inches tall, depending upon the device that you're measuring with. In terms of probability, that's just saying the probability of your value being exactly one number is always going to be 0. So we're going to be looking at probabilities not of single values, but of ranges of values.